All right, this is part 3 of limits at infinity. In part 2, we learned about a trick that you can use, an algebraic trick, to help clarify some of these limits of these big fractions and kind of get some of the junk out of the way, to either help you see what the limit should be better, or maybe just to make it a little clearer, like from a proof standpoint, so you can show someone else that your work has to be right. I'm going to use that same trick on both of these limits. Notice that it's the same function, top and the bottom one there. The only difference is we're asking the limit at positive infinity and negative infinity. And there's a reason for that with this problem. There's a little twist kind of in that second part that we'll talk about. As with all of these, I suggest as soon as you feel like you know what to do with one of these, pause the video, try to do it yourself, and then watch a little more to make sure you're on the right track. So in this case, you might just kind of be giving it a gut instinct here and looking at that first one, the limit as x goes to infinity, and saying, okay, what about the degrees? And maybe you're thinking, hey, the square root of x to the 6th, that's kind of like x to the 3rd. And on the bottom, we have x to the 3rd. And if you're thinking about it that way, that's a very healthy way to think about this one. You can actually kind of sniff out the answer that way. But I'm going to go ahead and use this trick that I'm talking about, which is to multiply the numerator and denominator of this fraction by 1 over x cubed. I'm going to do it on top also, but instead of 1 over x cubed, I'm going to use a different form. I'm going to multiply by the square root of 1 over x to the 6th. And I got into this in the last video. We have to again, though. The question is, are these two things equal to each other? Because what lets me do this is I'm multiplying by 1, right? I'm multiplying by something over itself so that I'm not actually changing anything. And so let's look at that. 1 over x cubed. And you know, I'm really just going to compare x cubed to the square root of x to the 6th, because the 1 over part is no problem, right? And that's the question. Are those equal? And the answer is kind of, right? In reality, if you plug in a negative value for x, then they're not equal, right? Then you would need to change the sign on one of these. Now, you could say the absolute value of x to the 3rd. Now this is a true statement, okay? It works. It always works for real numbers here anyway. But the absolute value is there for when x is negative, right? When x is positive, what does that absolute value do? Nothing. When x is negative, that absolute value will multiply a negative 1 on there. So I guess the question is, do we want to just throw the absolute value on down here? And I will say no, because we're talking about the limit as x approaches infinity. So what kind of x values are we talking about? Positive only. Since we're only talking about positive x values, we can actually leave off the absolute values there, and we can say, yes, these two things are equal for positive values of x, right? That way, this whole thing is equal to 1, again, for positive values of x, and so we are able to go ahead and multiply it that way. And so what we get is the limit as x approaches infinity. Let me just shrink this up so I have some room to work. We get the limit as x approaches infinity of, well, on top, if we distribute that 1 over x to the 6th into that square root, we're going to have the square root of 25, right? The x to the 6th cancel out. And then minus 4 over x cubed. And then plus 1 over x to the 6th. On the bottom, we're distributing the 1 over x cubed now, right? That version of it, because I don't have a square root down there. So when I distribute that in, I'm going to have 11 plus 2 over x minus 3 over x cubed. And since I'm taking the limit as x goes to infinity, anything at this point that has an x in the denominator is going to go to 0. And that's the beauty of this technique. All these terms go to 0. And so now I can say that this limit is equal to the square root of 25 over 11, not in a square root, right? So that's like a direct substitution technique now, right? We're plugging in like infinity, so to speak. I'm doing air quotes with the infinity. We're plugging that into the x's and the denominators. That makes all those little fractions approach 0. And so what do we get? We get 5/11ths as our answer, okay? We can do a very similar approach in this other limit down here. However, it's going to look a little bit different because now if we multiply by 1 over x cubed on the bottom, on top we want to multiply by the square root of 1 over x to the 6th. The problem is now x is negative, right? We're going toward negative infinity, and these two things are no longer equal unless we make one of them negative. I like to put the negative on the square root one personally because then it just kind of goes out front. It does not matter. They are opposites of each other without a negative there. So as long as you put a negative on one of them, you're good to go. And then if you follow through in the same fashion we did up there, you are going to get an answer of negative 5/11ths. That's what it'll turn into. Okay. One more problem I want to look at, because what if it's not quite in this form? This is a problem very similar to one from our textbook, Stewart Calculus. And, this one doesn't have a fraction. So how can we handle it? If you just do direct substitution, it looks like infinity minus infinity, which is an indeterminate form. And you might be tempted to say, well, hey, next to the x squared, ax, where a is a constant, doesn't really matter. Maybe it's piddly and insignificant, right? And same thing here with the bx. The problem is when they're not in a fraction like they were in those other problems, you can't just disregard those quite so easily, because we're going to be subtracting to a certain extent away these square root of x squareds, but not quite so simply, because there's other stuff with them, right? Makes it tricky. So that ax and that bx might actually matter, and in fact they do. We need a way to take this thing that is not in a fraction and get it into a fraction, because when you have a limit as x approaches infinity of a fraction, you have more tools, I feel like, at your disposal, right? You can kind of ask yourself, like, which term wins, right? Where's the highest degree term? So I'm just going to give a hint on this one and not finish it. If you want to turn this into a fraction, then what you want to do is multiply it by something over itself, right? And you want to pick that something very carefully. And ideally, what we'd like to do is pick something that'll get rid of these square roots. So if you have an idea, pause it if you want to think for a second. What you do is you multiply by the conjugate, right? So we'll take the square root plus the square root instead of minus, right? So in other words, the square root of x squared minus ax plus the square root of x squared minus bx on top and bottom. And if you do that, this is like over 1, right? On top, you now have a difference of squares, right? You have a minus b, a plus b, and you get a squared minus b squared, which means all those square roots go away beautifully. On the bottom, you'll have those square roots, and then you can actually use a trick like this, right, on what's left, okay? And so give that a try. I think that this one comes out to negative ax plus b. I think you're going to end up with b minus a over 2 if you do it correctly in the end. So see what happens. Anyway, that's going to be it for this video. Beautiful music there to end it. I hope that these were instructive with dealing with limits at infinity. There's a lot you can do if you know how to look at them. There's a lot you can do just by kind of looking at them the right way. But then there's some little algebraic tricks you can do to help you look at them the right way.